Hi, welcome to episode number 4 of the Zero Pages. This episode is going to be a little bit different because I'm going to be doing programming for our first game, or really just a program for the NES. We've gone through a number of concepts, and I think it's sort of the right time to start to put those concepts to use. So we'll begin by making a program that initializes the NES and makes Mario appear on screen. Now this video is going to be a little bit more raw than some of the other Zero Page episodes because I'm going to be doing this live so I can explain the bits and pieces in an environment that matches what you'd see while programming versus just showing a bunch of slides. To begin, let's look at the graphics that we're going to use, and they live in a file called hellomario.chr or char or character, however you want to pronounce that. So I've opened up a program called YYCHR, which is a free program you can download, and I've opened this char file here, and you can see that it consists of a number of 8x8 tiles that have Mario from Super Mario Bros. This first page that we see here is all sprite-related imagery, and this bottom page here is all background imagery, which we're not going to touch right now. Our goal is to initialize the NES and have these first 8 character tiles appear on the screen. One thing you'll notice is that the colors are all strange. So if I click here, you can see the top part of Mario's head looks a little bit odd, and if I click around on the palette, it changes based on whatever palette I've selected here. And that's because the color information isn't actually stored in this character file. What's stored is an offset into a palette, and so depending on which palette I have selected, the different offset is selected. So for example, this is pixel 0, which corresponds to this 0A color here in this palette. Now, that's not necessarily the right color, but we'll take care of that when we start working on the program. In fact, this color palette looks perfect, right? This is what Mario looks like, with the exception of maybe this background color. That's not exactly what we want, but that's roughly what Mario is supposed to look like, right? So we'll have to make sure that our palette is the same so that Mario looks correct when we load him on screen. So the first thing we want to do is we want to get things set up so that we don't have to type the commands out to build the program every time. We can make use of a batch file to do that for us. I have an empty batch file here, and what I'm going to do is I'm going to have it run first CA65, which is the assembler, which you hopefully downloaded after watching episode 1. And I'm going to have it assemble hellomario.asm, and then I'm going to use the -O option to have it generate an output file called hellomario.o, and then I'm going to do --debug-info. This tells the assembler that I want debugging information to be generated for this program. The next line we want is we want to invoke the linker. The linker, LD65, will take the .o file and turn it into a .nes file, which can be run in an NES emulator. So we write hellomario.o. We want our output to be hellomario.nes. We specify the T flag for the type, which is NES, and then --debug file, which just tells it where to put that debug information that we want, and we type hellomario.dbg, and then we're done. Now that we have our batch file that's going to make the program, let's start with the actual assembly code. When starting your code for the NES, it has to be organized into what are called segments. Segments are definitions for the assembler to help it understand where different information about your program should reside in memory. In a real NES cartridge, that maps to an actual physical address that the NES CPU is using to find your program code and your image code. On an emulator, it's more about the assembly code being positioned in a place that makes sense for the emulator to run it as if it were a real NES cartridge. So there are several segments that we have to define for the assembler in order to be able to have our program work. So let's start with defining the segments. The first segment is called the header. And this is where we define what's called the iNES header. And the iNES header is what helps an emulator understand what your program is, what your game is, and how it's meant to run. This isn't required for a real NES cartridge, but if you're using something like an EverDrive or running your code on an emulator, you need this header in order for it to understand how to run your game correctly. The next segment is probably going to sound familiar. It's called the 0 page. And the 0 page is a location in memory that begins at memory offset 0 and goes all the way to memory offset FF. And it's called the 0 page because when you address memory, normally you have 2 bytes. You have the most significant byte and then the least significant byte. This 6502 has a special mode where if your memory is within 0 to FF, it doesn't require the use of this most significant byte. It can shortcut the command and use just the least significant byte in order to fetch information and store information from memory. So the term 0 page refers to the fact that that first most significant byte is the value 0. The next segment is called startup. And this is where your code starts. Now, this segment's important because it defines where it's okay for you to write your code. This is different than where the CPU starts to run code. This is purely an organizational segment that identifies where your code lives in this file, and then the assembler knows where to place it on your ROM or your, if you want to think of it as a virtual cartridge, so that the CPU can execute it when it's running in an emulator or on an actual piece of hardware. The next segment is called vectors. And this segment defines some special addresses that the 6502 needs in order to operate. And we'll get into that in a moment. It's just important to make sure that we have it. The final segment is chars. And that's where we tell the assembler where to find the graphical data. And in this case, we tell it to find it in hellomario.chr. Now, these segments are the ones that are defined by default by CA65. They're named according to the convention that the writers of CA65 and other programmers have gone with, but they don't have to be called that. And while it's outside of the scope of this video, I will say that you can modify the NES configuration file for CA65 to define different segments. And that's important for when you're writing for other types of mappers like MMC3, where you need to be able to define different segments that start at different memory addresses. Again, beyond the scope of what we're doing here today, but important to know that these are just sort of labels that have been given to memory addresses and can be changed as necessary when programming your game. So going back to the header now, we need to actually put some data in there. So what we need to define is the information that's required for the iNES header. So that information is readily available on the NESDev programming wiki, where you can find a definition of what all the bytes mean and why they're there and extensive detail. But for the sake of this video, I'm going to just kind of go through them real quick and explain what they are, and then we can follow up on them in future episodes of the 0 pages. So the first thing we're going to do is we're going to define this string of bytes, NES, which is the beginning of the header of the iNES header. The next thing we're going to do is define the value 1A. And this is the signature of the iNES header that the emulator or the EverDrive is going to be looking for when it loads the ROM to ensure that it's a file that, at least from this perspective, looks like a normal ROM that it should be able to load. The next byte that we're going to define here is how much prog ROM or code ROM we have on our virtual cartridge, on our NES ROM file. And so we're defining that there are two 16 kilobyte ROM spaces for a total of 32 kilobytes. The next thing we're defining is that there is one 8 kilobyte character ROM location on our cartridge. And again, this is all defining things that in a real cartridge wouldn't be necessary because you'd actually have two prog ROM chips and one char ROM chip or one RAM chip or whatever the case might be for your particular game. We have to define this because there are no actual physical chips in our code, right? This is just, we're making a file that defines our game, and we're telling the emulator that this is what it would look like if it were a real game on a physical cartridge. The next thing we're defining here is information about the mapping and the mirroring. And in this case, we're not doing anything fancy, so we're just going to leave this all as zeros. And I'm putting this in as binary directly rather than as a hexadecimal value, because later on we may want to come in and modify it, and it's a little bit easier to see this as a binary representation than a hex representation, at least for me. The next several values are going to be set to 0 because they don't apply to what we're doing. And again, all of this is defined in the NESDev wiki if you want to see what those bytes do. For the sake of this video, we're going to leave them 0. And then the final 5 bytes we define here are filler bytes. They don't do anything, they just need to be put in there so that we fill up the appropriate number of bytes in the header. The next thing we're going to modify is the vectors segment. And the reason we're going to do that is because it doesn't really make sense to modify anything else or write any other code before the vectors have been set up properly. A vector is just a fancy way of saying we're going to define how code gets called if a particular type of interrupt happens. And an interrupt is exactly what the name implies. It interrupts the current flow of code to cause something else to happen. So in the vectors segment, we can define 3 interrupt handlers. And the interrupt handler is, as the name again implies, code that handles what to do when an interrupt occurs. The first interrupt handler we're going to define is the one for the non-maskable interrupt. The non-maskable interrupt is what occurs if it's enabled when the PPU begins the process of VBlank, which is when the scan gun on a CRT will be going from the bottom of the screen back up to the top. It's the time between the image being on the screen and then being refreshed again by the electron gun. So because we're going to use that in this program, we're going to update the vectors to point to a label that we're going to name NMI. And we'll get to the definition of that in a moment. The next interrupt handler that we are going to define is going to be named reset. And that's because the second vector that we can define is what happens when someone presses the reset button. So you're playing a game and you die and you're trying to do a no-death run. You hit the reset button. What happens? Well, the CPU comes to this vector section and it looks for the second entry that says where it's supposed to go when the reset button is hit. And that's going to be a label named reset. The third and final vector is for when specialized hardware triggers an interrupt. We're not going to define anything here because we're not using this for anything in our program today. But if you're using a mapper like MMC3, for example, you can set that mapper up to provide you with an interrupt after it's counted drawing a certain number of lines on screen. And if you needed to know when that occurred, you could set a interrupt handler at this position here in the vector segment to get called when that occurs. Again, not something we're doing today, but I figured it's worth mentioning. Okay, so we have our vectors defined, so we know what the program is going to do when we reset the NES and also when the screen is being redrawn. So let's get started. Let's define our reset handler. And let's define our non-maskable interrupt handler. Both of these labels, they may look very straightforward, and you might be thinking, well, how does that do anything? But what we're doing is we're giving the assembler locations in memory that map to these names, reset and NMI, so that the vector now has those addresses when it goes to assemble your code in such a way that when either of those interrupts occur, it can jump from the current location in memory that the CPU is processing and go to either of these labels. One thing we want to do is when we're done with processing all of our code that happens at reset, we want to put the CPU into a loop. And the reason we want to do that is because we're just initializing some memory and then we're done, and everything else is going to be handled in the non-maskable interrupt. So let's write the code for that. So I'm going to define a label named loop, and then I'm going to use the jump instruction, which will branch right back to loop. So we've created an infinite loop here that makes sure that our code doesn't come to this position and then go into the non-maskable interrupt code accidentally. With the non-maskable interrupt, and in fact any interrupt handler, we need to return from this call here in a different way than you might normally return from something like a subroutine, like a function call basically. The way that you do that for an interrupt is RTI. Now, if this were just a standard subroutine, like a helper function that does something for you in your game, you could use RTS, right? But because this is a special interrupt handler function, we have to make sure to use the interrupt return. All right, so when the NES turns on, things are basically in a random state. We have no idea what the memory values are. We have no idea what the CPU is trying to do. There are some initialization things that the hardware does, but in general, it's not really in a good state for us to start using. So the first thing we want to do is initialize things so that the NES is ready to be used for our game. Well, how do we initialize it? There are a few things we have to do. One of the most important things we can do is zero out all the memory for the NES to make sure that there's no random junk in memory that might cause us problems as we move forward with developing our game. So even before we can do that, though, we have to get the NES into a known good state where we can reliably operate. Let's start by first running SEI. SEI disables all interrupts on the NES. Now this is important because we don't want anything coming in and interrupting our code as we're trying to initialize, trying to play game code, right? We don't want the NMI operating just because we had put some code in there and we didn't disable the interrupts. So it's very important to turn the interrupts off when we first start. The next thing we need to do is we need to disable decimal mode. Now, the reason we want to disable that is because the NES doesn't actually support decimal mode for its math. The 6502, some models did support doing math in a decimal mode, but because the 6502 on the NES doesn't have it, our best bet is to just disable it so that it doesn't cause us any grief by having it turned on. The next thing we need to do is disable the sound IRQ or interrupt requests. Now, we're not trying to do anything with sound, so we're going to leave it turned off, but when you start your game, you want to make sure that the sound IRQ isn't enabled so that as you load data into memory, that random sounds don't start playing. So all we do is we load the value 40 into the X register, and then we store that into memory address 4017. Now, the value of that 40, again, can be looked up on the NESDev wiki, where it will show that the interrupt request bit for the register at 417 in the APU, if it's set to 1, disables the sound IRQ, and if it's set to 0, we'll enable it. So we're setting this value here as part of our initialization, and that will ensure that no random strange sounds start playing when we start loading up our game code. The next thing we need to do is initialize the stack register. Now, we're not going to be using the stack register at all in this program because we're not really doing anything super complex, but it's good to get in the habit of initializing this register because eventually we will be using it, and the code we're writing here may serve as a boilerplate for all future projects, and so we want to make sure that we're doing things the right way so that we have a clear starting point for anything else we do, and we're not introducing bugs early on as we start coding. So what we're going to do is we're going to load the value FF into the X register, and we load FF because the stack register, as you push data onto the stack, decrements the value, so it'll go from FF to FE to FD and so on, and then as we pop things or pull things off the stack, we'll go back from FD to FE to back to FF. So we want to load X with FF, and then we want to transfer the X register over to the stack register. And then we're going to do something a little bit clever here. It's just a little trick where we increment the X register, and by doing so, when we go FF plus 1, what that gives us is 0, because the byte rolls over. We can't represent anything bigger than FF in the X register, and now we have the value 0 in X, which is what we want in order to zero out a few values in the next step. The next thing we want to do is we want to turn off all drawing on the NES so that we don't get any weird random graphics before we're ready to display anything while we load data into the PPU. So what we're going to do is we're going to zero out the PPU registers. Now the PPU registers that we primarily are going to be using for this purpose are at address 2000 and 2001. And if you want to see the details of what those registers can do, I'll show an image of what it shows on NESDev right now. But let's just suffice it to say for this moment that when we set those two registers to 0, we're turning everything off on the PPU. So I'm going to store the value of X, which is 0, to address 2000. And then I'm going to do the same thing again to address 2001. Now note, there's a really important difference between writing a value with the $sign and a number after it versus a $$ and a number after it in hex. And if you have the pound character here, what you're saying is I'm loading a value. If I got rid of this pound, what I would be saying is then I'm loading the value at address FF. So two very, very different things. So it's always really important. Make sure that if you're dealing with a number, you have the pound, and if you're dealing with an address, you have just the $sign. Note that above it's a little bit confusing because the byte section uses the $, for a value, but that's only for that kind of a section. Now that we've zeroed out our PPU registers, we need to do one more thing, and we're going to disable the PCM channel so that we don't get any other possible weird random sounds to occur as we load our data. So we're just going to store X one more time into address 4010. Okay, so now we've made the NES basically safe for us to start doing anything. The last thing we need to do is we need to wait for the PPU to do its initialization and give us one VBlank period. We need to make sure that the NES will attempt to draw at least one screen worth of data. And in this case, it's going to draw nothing because we've turned off all drawing. It's just going to draw a blank screen. But we need to make sure that we have it try to draw that one blank screen before we start doing anything, because that's our indicator that the system is ready to start running our game. Okay, so now we're ready to wait for the VBlank. The first thing we need to do is we need to read from register 2002. Now, normally we might do something like load A with 2002, and then look at the value that gets returned to determine if the VBlank has occurred, because register 2002 tells us if the PPU is currently drawing the screen or if it's in the period of VBlank where it's waiting to draw the next screen. And that's determined by bit 7 that's returned in the byte from 2002. There's a trick that people use for determining this, and instead of using load A, we use the bit opcode. Now, the bit opcode tells us a few things. The most important thing that it tells us is what the value of bit number 7 in 2002's return byte is. If bit number 7 is set to the value 0, then we're not currently waiting to draw the next screen. If bit number 7 is 1, though, then we are, and that means that we've reached the period where we have drawn a full screen and we are now going to draw yet another screen, which means that we're good to go with what we want to do. Using the bit command, we can get bit number 7 from 2002 and then evaluate that value to see if we should branch back or continue on. The way that we do this is pretty complicated, but it's actually not very difficult to use. So bit number 7 gets stored in a sign bit, and that sign bit is set when doing a mathematical operation results in a negative value. In this case, we can use that to our advantage to use a branch operation called branch plus, or branch if positive, to have it jump back if the bit in bit number 7 is set to 0. Because if the bit is set to 0, then we're not in a VBlank, which means that branch if positive will want to do the branch. If it's set to 1 because we are in the VBlank, then branch if positive will think that it shouldn't branch because the negative bit will be set, the sign bit will be set, and then therefore continue on in the code. Now, we're going to use what's called an anonymous label, where basically we're just going to put this colon here, and then we're going to say, after the BPL, we're going to say colon hyphen, which basically says, okay, if you branch back to the previous anonymous label. You can do a similar thing where you branch to the next anonymous label using a plus, but because we're branching backwards, we're going to use the minus. Now, this is something that I recommend you use sparingly because it can get confusing, but in a situation like this where you have a very simple little bit of code where you need to do branching, it can be really handy so you're not coming up with all sorts of crazy labels. Okay, so now that we know that we've done one full render of the screen and we're in the VBlank period, let's start clearing out the memory on the NES. So the first thing I want to do is transfer the value of the X register, which is 0, to the A register, because we're going to use the A register in this process of clearing out the memory. The next thing we're going to do is we're going to define a label called clearMem, and we're going to use this for the loop of clearing out our memory. Now, again, we could probably have used an anonymous label, but because we're doing a very specific task and the anonymous labels tend to get confusing, I try to use them pretty sparingly. The next thing we're going to do is we're going to write the rest of the loop before we start storing things into memory, just to make sure we have the condition properly configured. So the first thing we're going to do is we're going to increment the X register, because that's going to be our counter into the memory that we want to initialize. We're going to write branch if not equal to clearMem. Now, you might say, not equal, what's not equal? Well, this is another little trick that you can use when programming in 6502. When you increment the X register, it will increment from 0 to 1 to 2 to 3, all the way up to FF, which is the value 255 in decimal. When you increment the value FF, it rolls over back to 0 like we saw previously on line 26 there. But we have the ability to use the fact that it rolled over to our advantage. The CPU, when it rolls over the value, will set what's called the 0 flag, which we've talked about in other episodes of the 0 pages, and then that will allow us to use these branch, if not equal, opcodes to determine whether or not we actually rolled over the value of x back to 0. And the reason for that is that when you do a comparison of two values and they're equal, the 0 flag is set to 1. And if they're not equal, then the 0 flag is set to 0. So adding 1 to FF actually results in the same thing as comparing two equal values. The value of the 0 flag is set to 0 every time you increment this x, except when you increment it from FF to 0, 0. And then the 0 flag gets set to true because the value of the operation resulted in a 0, in which case we have the ability to continue on past this branch if not equals. Again, it's a little trick that we use commonly when we're programming in 6502, and if it gets confusing, let me know and I can do a little bit more content on explaining how all of this exactly works. Now we have our loop that's going to increment the X register all the way from 0 to 255, and then it's going to roll over to 0 and then stop looping. So let's actually initialize the memory. So we're going to start in the beginning with the address 0, and we're going to use the X register as our index into this memory range. Now remember, X can only be the value of 0 to 255, and that value is going to be added to the address that's stored in the first part there before the comma, resulting in the range of 0 to FF, or 255. So that's not going to clear all of our memory because the memory is 2 kilobytes, which is 800 in hexadecimal. So what we have to do is we have to store the value of A in ranges in order to clear out the entire thing. And we can't rely on X to do it for us because it can't increment past 255. Thankfully, this is no problem, and what we do is we say, okay, next we're going to use range 100X, and that's going to give us the address range of 100 to 1FF. And we're going to do the same thing for 200, and that gives us 200 to 2FF, and then we're just going to keep doing this. So 300, 400, 500, 600, 700, and we're done. Now, I'm going to change this a little bit for a reason that I'll explain here, but you won't see for a little bit. One thing that we need to be able to do is store information about the sprites that we want to display on screen in a range of memory. And on the NES, the sprite data takes up exactly 256 bytes for all 64 hardware sprites. So what we're able to do is choose one of these ranges of 256 bytes to store the sprite memory that we need to copy into the PPU when we want to draw the sprites on the screen. Now, the important thing beyond that to remember is that when you're working with the PPU sprites, you have to refresh that memory every single frame of the game because the NES uses what's called dynamic RAM. And dynamic RAM is a cheap form of memory that was a good way to cut the cost of the NES, but has what's called decay, which means that if you don't refresh the value every cycle, the values in the RAM will actually start to degrade and give you essentially random data. So you can't just update that OAM data once for the sprites and then hope that it will persist over the next 3 or 4 seconds that you're displaying your data. Instead, you have to update it 60 times a second every frame that your game runs. So we need to set aside an area of memory that's going to have the permanent information that we're going to use to update the PPU sprite information. And what we're going to use for the purposes of this program is range 200 to 2FF. The reason that we need to set this aside is we need to initialize this to a value other than 0 so that sprites don't appear on screen even though we don't need them to be there. What we're going to do is we're going to take this range out of this part of the loop, and then we're going to load A with the value FF, which is what we're going to initialize that memory range to. And then we're going to do the store here, where we're going to store the value FF into 200 to 2FF. After we're done with that, we're going to load A with 0 again, so that when we branch back to the beginning here, we will continue to update these memory ranges with 0. Now, we could have done this in 2 separate loops, but that's inefficient and unnecessary. If it makes it clearer for you, then certainly you can do that, but generally speaking, games will do this all in one shot, just switching the value of A from FF to 0 back and forth in order to initialize the range of memory that's required. So now the next thing we're going to do is we're going to wait for a VBlank again, just to make sure the PPU is really ready for us to start putting data into the PPU. So here's what I'm going to do. I'm going to take that code we wrote and I'm going to just copy and paste it here. And now we're going to do the same thing. We're going to wait for VBlank again. So this is our second time waiting for the VBlank. And once that's done, we're ready to go and start interfacing with the PPU. Now that we've done that, let's start by updating the sprite memory so that no weird sprites appear on screen while we're trying to initialize our game. This is more of just getting a clean shot of memory into the PPU to start off with. By the time we actually display things on screen, we're going to need to refresh it again, but this is just kind of a common practice. So what we're going to do is we're going to load A with the value of 2, and this is going to tell the PPU what range of memory the most significant byte, starting with 02, like you can see here, this range that we're initializing to FF, we're saying, okay, this is the most significant byte of the memory range, the 02, that we want you to read into the sprite memory, starting from 0200 to 02FF, and then we're going to store that into the register at 4014. And then once we've done that, we're going to use this opcode called NOP, which is basically shorthand for no operation, and that just burns a cycle basically. And the reason you need to do that is, as I understand it, the PPU really needs a moment to be able to initiate that memory transfer from the range 200 into its own memory, and so we just burn that CPU cycle in order to give the PPU a moment to do its thing. Now that we've initialized some things and we've got the CPU ready and the PPU ready, let's start writing some palette memory so that the things that we put on screen actually look correct. That's done by telling the PPU where in its memory we want to store data. That's right, the PPU has its own memory that's separately addressable versus the CPU. And we can't address it directly, we have to do it through a PPU register at the address 2007. And before we can do that, we have to tell the PPU what range of its internal memory we want to update. We're going to start by loading the value 3F into A and then store that into 2006. Loading that value 3F and storing it into 2006 tells the PPU that we want to start off writing data at a memory address, and we're giving it the most significant bit, or the first part of the address that we want to write at. In this case, what we want to do is we want to write to address 3F00. So we have to tell it, here's 3F, that's the first part. Now load in the value 0 and store that into 2006, and now the PPU goes, aha, you want to write to 3F00, and now it's ready for us to start writing palette data into the palette memory of the PPU. Before we do that, we're going to initialize the X value for our loop, because we're going to need that to count through and make sure we load only the appropriate number of palette values. Now that X is initialized and ready for us to load palette data, we're going to create our label called load palettes. Just like before, load palettes is just a label that we're going to use to jump back as we load the data about the palettes into the PPU. So let's start by writing the loop information first, and then we will go back to the actual functionality of how we write the palette data. So the NES PPU supports two sets of palettes, one for the backgrounds and one for the sprites, and each of those have 4 separate 4-color palettes for a total of 32 colors. The one caveat there is that color number 0 in every palette is the same. That's the background color. So no matter what palette you're working on, if you set color 0 to a value, it's going to affect every single palette's background color. But that said, let's write the loop so that we increment to 32, and then when we're done, we will stop looping. So what we want to do is we want to increment x by 1 every time, and then we're going to compare x to the value 32 hex, which is 20 hex, which is 32 in decimal. And if the value isn't equal, branch if not equal to load palettes. That's pretty straightforward as far as loops go, but where is our palette data coming from? One of the things we can do when working on a program for the NES is we can define data directly in our code. And in this case, what we're going to do is we're going to define the palette data that we use for this program directly in our code after the NMI label here and after we do our return from interrupt. So I'm just going to paste this data in. So what we've done here is I've just pasted in this text, and it defines a label called palette data. And then it defines one set of 16 bytes, each of them defining a single palette entry with the different colors that we want in the palette. So this is one 4-color palette, this is another 4-color palette, and you can see that each of them begin with the value 22, and that's because that's the color we want for our background. And I've got the background palette data and the sprite palette data. Alright, so now that we have our palette data here in the file, what we need to do is actually load this into the PPU. We do this by doing a load A with our palette data, and then we're going to index by X. So what we're saying is go to the address defined by this palette data label, and then increment the value of that address by the value in X currently. When we start the loop, that value is 0, and so we start here at this first entry, which is index 0. Yes, it's 0 indexed like in C and other languages, which I know is confusing, but you just got to remember that this is the first entry, it's index 0, this is index 1, this is index 2, and so on and so forth, and it will continue on until we've indexed through all 32 values. We load A with the value of the address of palette data plus X, so that gives us, in our first index, we get the value of 22 into A, and then we're going to store that into address 2007. Now 2007 is the corresponding register that goes along with register 2006. So above, we had stored the value 3F and 00 into 2006 to tell the PPU that we were ready to start writing values to the address 3F00 in the PPU memory. And that location, 3F00, is the location, the beginning location of where palette information is stored in the PPU. Once we've done that, writes to 2007 will write into that memory address. Now, the cool thing is that doing this one write into 2007 will increment the value that the PPU is writing to. So the first time we do that store into 2007, we store into 3F00. The next time we store into 2007, it'll be in 3F01 because the PPU will have incremented the address to go to the next address in that memory. And the subsequent time it'll be 3F02 all the way until we get to 3F20, which means, 3F1F, which means that we are complete and we've updated all 32 bytes of memory for the palette. So that's not so bad, right? Like, we're just looping through and we're reading 32 bytes of data and we're storing them into 2007, which increments this memory range for us in the PPU and loads the PPU with the data that we want for our color palettes. Now, for the sprites, as I mentioned before, the NES uses dynamic RAM, so we can't use the RAM directly like we do with the palettes, because if we load that data in, then what'll happen is the sprite might display for maybe a frame and then disappear, which is no good. So what we're going to do is we're going to load the information about the sprites into the range 200, which we set aside earlier here when we initialized it this way. And we're going to load that in so that when we go into the process of updating the sprite data every frame, we will draw Mario on the screen. Just like before, we want to load X with the value 0. We're going to create a label called load sprites. And it's sprites plural because the NES has only 2 modes of operation. It can only either display an 8x8 sprite or an 8x16 sprite. In this case, we're using the 8x8, so Mario is actually composed of 8 total hardware sprites, right? There are 8 8x8 tiles that are used to make the one Mario sprite. After I've defined this label here, I'm going to increment X, just like before. I'm going to compare it against 32 because we want to increment through the memory that defines the sprites, and I'll get to that in a moment, why that's 32. And then we're going to branch if not equal to 32 back to load sprites. So I just said that Mario is composed of 8 sprites that make up his image in order to display on the screen properly. Where did this 32 come from? Well, the OAM data, or the sprite data that's used to define how sprites are displayed on the NES, actually consists of 4 bytes per sprite. The first byte is the Y coordinate, or where from the top of the screen to the bottom of the screen the sprite appears. The next byte is which tile to display, and the tile means which graphic that we looked at in YYCHR is what we want to display. So if we look again, this is tile 0, this is tile 1, this is tile 2, this is tile 3. And so we need to define which value we want the sprite to use in order to tell it which tile we want selected for that sprite. The next value is a bunch of different attributes that I'm not going to go into because they're not relevant to what we're doing today in this video. We'll go more into it as we cover more advanced PPU techniques and topics. And then the final byte, byte number 3 of the 4, again 0 indexed, is the X coordinate, which is where the sprite appears from left to right on the screen. If you have 8 sprites, and they're 4 bytes apiece, that's 32 total bytes. Now, just as before with the palette data, we can define the sprite data directly in our code and sort of simplify things so we don't have to do any weird calculations or try and figure out all of the placement by hand. Instead, I can take this data that defines where the sprites should appear. So for example, this set of 4 bytes represents the first sprite, and it says that it's offset in the y-axis by 8 pixels, it's tile number 0, and it's offset in the x-axis by 8. And then the next sprite is also offset by the y-axis by 8 pixels, but it's tile number 1 instead of tile 0, and then the X offset is 16 instead of 8. And so we're building this grid of 2x4 tiles to represent Mario. So just as before, we're going to go back and we're going to load the data from the location sprite data into the memory at 200 rather than into the PPU memory. So we're going to load A with sprite data x. Again, remember, it's take the address at sprite data and then add to it the value of x. And so when x is 0, it's going to be this first byte, and then when it's 1, it's this next byte. When it's 2, it's this byte here. When it's 3, it's this byte, and then this is going to be at byte 4, etc. So we're loading that value into A, and then we're storing the value into address 200 offset by X. So this is really nice, right? Because we don't have to do any crazy math to get the X offset properly matching or anything like that. We've arranged the data here to match the exact format required by the NES in order to make this really, really simple to work with. So we're loading the value, we're storing the value, and we're good to go, right? So we do our increment, we compare it to 32, and if it's not equal, then we go back to the load sprites. Great. So now we're done loading our palettes and setting up our sprites in order to display. Now that we've loaded all our data properly, we need to be able to turn on drawing so that we can actually see everything we loaded. So you do that by enabling interrupts, and it's really important that you do this. I've had problems where I forget to turn on the interrupts, and then what happens is it looks like nothing is working, and you spend a lot of time trying to figure out why what should be drawing and working is not. So you make sure you enable your interrupts, and then what we're going to do is we're going to load the value of 10010000, and I did this in binary to make sure that we can talk about the individual bits properly. We're going to load this value into A. So what this is doing is we're going to store this value into the address 2000, and this bit that's set tells the PPU that we want to be interrupted when the VBlank is occurring through the non-maskable interrupt here. Right? So when a VBlank occurs, the CPU will stop anything it's doing and bring us to this point in our code, which is good. That's what we want to do because we want to be able to do certain things like reload the sprite memory when we're about to draw yet another frame to make sure that our sprites actually look correct on the screen. The next thing we're going to do is we're going to set this bit here to 1 because we want to tell the PPU that the background is not using this first screen of data to draw the background, but instead is using this second screen. And the reason that's important is because I've deliberately made this tile be empty and be filled with the transparent color. The reason that I want that is because I don't want to be going into how to set up the background right now. It's a little bit more complicated. So we need to make sure that we're looking at this tile set so that the background is empty when the game is running. So now we've told the PPU to enable NMI and change background to use second char set of tiles, right? And that's basically telling it to use address 1000. The next thing we need to do is we need to actually turn on drawing because we've turned it off by initializing register 2001 to 0. So what we're going to do is we're going to load A with the value 000111110. And what happens with these bits set in 2001 is we are enabling the first 2 bits starting from the least significant side. These turn on drawing of background and sprites for the leftmost 8 pixels, enabling sprites for left sprites and background for leftmost 8 pixels. And then the second set of bits here, 1 and 1, simply enable sprites and backgrounds in general, right? So we're telling the PPU, yeah, it's okay to draw the background and it's okay to draw your sprites. So we've loaded all the data we needed to ensure that the CPU is ready to go. We've updated the data for the PPU so that the palettes are set. We've set up the CPU memory for our sprites so that we have something to copy into the PPU to display the sprites. And now we're going into this infinite loop we created before because we're done here. We don't have to do anything else. We're not doing any game logic. We're not handling controllers yet. So there's nothing else we need to do here at this point. The next thing we need to do is we need to actually have some code here in this non-maskable interrupt handler. And what we're going to do here is very simple. We're just basically going to tell the PPU to copy the data in the range 200, which is our sprite memory, into the PPU so that sprites are properly displayed. So we do that the same way we did in the other location earlier when we were doing our initialize. We're going to load A with the value of 2, and then we're going to store that value into 4014, and that's going to tell the PPU, okay, copy the data, copy sprite data from 0200 into PPU memory for display. And that's it. We've written our code to initialize everything. We've set up our sprite data. We've set up our palettes. We have our sprite data here and everything. So now we should be good to assemble this code and see what happens. So I'm going to run the batch file called make. So I'm going to run this, and now we should have our NES file, which we do. It's called Hello Mario. So I'm going to run that, and that's going to launch Messin, and there's Mario displaying on the screen with the proper colors and the proper background. So I realized that some of this covered some complex topics that we haven't covered in depth, but I know also a lot of people really wanted to see a getting started sort of hello world program. And this was the most basic way that I could present this in a manner that made it exciting, that you could actually see something happen when you were done beyond just that blink test program that I initially supplied for Zero Pages episode 1. Now that we've done this, we're going to sort of backtrack and look in more detail at the PPU and what its capabilities are and how it interacts with the CPU in more detail to hopefully understand how this all works a little bit better. I hope this was helpful. I hope this was clear. If you have any questions, of course, reach out to me. I'm on Twitter at Clairvis. I'm on Nintendo Age as Zelius. You can email me at zelius@gmail.com. And be sure to keep an eye out for the next episode of the Zero Pages. If you have a specific suggestion of what you'd like to see, please let me know. And as always, thank you for watching, and I will see you on stream or in the next video. Take care, and thanks.